Thank you for letting me speak in the seminar of my own group. I only had to book like 2 months in advance. I'm very happy to be talking about this project. Dario Cavallaro, who's one of the first collaborator on this, was here I think a month ago, and this was when we finished this project, and it's about to go on archive. Let's say this month it should be there. The title on archive would not have the Oort cloud comment. I just want this for the talk because I think it's funny. This is from Dimitrios. Also working on this is Stefan Kreuzer, also from the TU Berlin, and Sebastian Wieler, for whom I drew the Keist thing. I'm very happy with this Keist thing. And I'm kind of going to start with how this joke works, like what I mean by Oort cloud, what does this have to do with disjoint paths. So I'm explaining Dimitrios' joke to you to start with, and then I'll get into what I mean by disjoint paths. So let's start with a map of the universe. Oh no, actually. Let's start with a map of the universe. Wrong universe. So this is a map of the universe. And somewhere in there is us, right? We're in the Milky Way galaxy, and maybe to be specific, like we're somewhere there. And if you zoom in, then this is a little bit too far, but if you zoom in like a little bit less, then you get to kind of a view of slightly outside of the solar system. So this is the solar system. This is how far humans have roughly gotten. This is Voyager 1. And this is the Oort cloud. But the Oort cloud is still not like the next solar system over, right? It's not Alpha Centauri. It's still close to the solar system. And if I was to categorize some algorithms by closeness to the solar system, I would say that maximum flow is in the solar system, like it's nearby. Maximum flow is nearby. We can do this efficiently. We can get there like within a lifetime. And let's say MSO model checking on bounded tree width graphs, so Corsair's theorem, this is not in the solar system. This is not even in the Oort cloud. This is somewhere in the galaxy. In other words, it's a galactic algorithm. And by now, what I want to tell you today is that actually k-Disjoint paths is somewhere in the Oort cloud, so it's close. It's not in the solar system. It's not maximum flow, but it's close. So this is the Oort cloud joke. So how do I get to this galactic algorithm thing? For this, we kind of have to pull up some quotes. This is kind of an old comparison that people have made. Specifically this one, this is from Johnson, I think, in the 80s, when Robertson and Seymour announced results about graph minors. He said, well, they have some algorithms, but unfortunately for any instance of a graph that one could fit into the known universe, one would easily prefer number of vertices to 70 to even constant time if the constant had to be one of Robertson and Seymour's. So at the time, people were complaining that they have algorithms and they technically exist, but if you wanted to run them, they're awful. They're technically polynomial time, but not really good in any sense. So let me give you a little timeline of what they did, just so you have a little bit of context for what I mean by Robertson and Seymour. So these are the papers in the Graph Minor series. I kind of put them in a color that's a little bit harder to see because I will reference them sometimes, but they're more for context. So this is 23 papers kind of establishing a lot of very fundamental results for FPT stuff and for graph structure theory. And somewhere in those, I will explain where later, there are algorithms that solve very fundamental problems. Now, the problem with those algorithms was that, as said below, they don't really run well, and then somebody came up with the idea to call these galactic algorithms in the sense that they don't really fit into our universe. So kind of fitting this quote from below. But this is with constants and with the runtimes that Robertson and Seymour were able to prove, right? So these are kind of old estimates of how bad these algorithms are. So maybe I should first explain to you what the algorithms are. So there's two problems I'm going to focus on, really only one problem, but I can immediately tell you how the other one relates. And the first is the k-Disjoint paths problem. This one's very natural, I think. You can probably imagine how you would use this to solve certain algorithmic problems. You're given a graph, some pairs of endpoints. Here I marked them, same color is the same pair. And I'm asking, are there, in this case, 3 disjoint paths that are pairwise vertex disjoint that connect these endpoints? Here there are those. I drew some. But in general, it's pretty difficult to solve this problem. I'll show you how difficult in a moment. And the other problem that a lot of people are interested in is minor containment. This is maybe a little bit harder to see. It's a little bit less fundamental in the sense that maybe you don't immediately know how to do something with a minor, but we'll see how to do something with a minor over the course of this talk. So what is a minor? A minor is constructed from some subgraph of a graph via edge contractions. This may be a little bit not so great to imagine how this lies in a graph, so I want to talk maybe about a minor model. So you can see a minor by kind of saying, I'm going to contract this part of the graph, for example, the orange stuff into the orange stuff into the small 5-vertex graph up above, and the blue stuff into the blue stuff, and then I'm kind of modeling the edge relation by seeing which edges are between the blobs, the colored blobs. So this is a model of a minor in this sense. And the problem that we can have is, I want to know, given two graphs, is one a minor of another? So here it might be more obvious why this should be difficult, because there's a lot of different things to try, right? Different ways to choose blobs and then check whether they actually realize the edge relation of the minor you're choosing. So I want to mention once, because I don't think I will have time to explain this in full generality, that actually what we're doing is on folios, which is a generalization of both. It's probably not easy to see how you generalize both. If I have some time in the end, I will tell you a little bit about that. But technically, all of this is in a much more general setting, which is much harder to understand why it's the sensible setting. So I'm going to stay with disjoint paths and sometimes with minors just to make it more easy to draw and imagine. Okay, so what about these two problems? Are they hard? I'm going to focus on k-disjoint paths. It turns out that we knew even with the first, I think it was 23 problems by Karp, this was one of the problems that we knew were hard. If I give you a k-disjoint paths instance, so some set of pairs of vertices in a graph, without telling you what k is, or without letting you choose this as a parameter, then this is going to be hard. In fact, by now we know this is even hard on split graphs. So you can see first it was found that it was just hard on general graphs, then you got this down to planar graphs, then we got to circular arc graphs, even more simple graphs, and then we got to split graphs. And in all of these classes, it's hard if you don't have k as something that you can kind of fix as a constant. So k is the number of pairs that you're trying to combine. But what if you do put it as a constant? What if I allow you to do some wild computations in the number of pairs you want to connect? So people tried this early on for planar graphs and for planar digraphs. And I am missing attributions here, I think. I'm very sorry about that. And in those two settings, this does work. Here, the first one we would call fixed parameter tractable, where the f of k, so the wild thing you're doing in k is multiplicative to n, and the other one is called xp, so there you're doing wild stuff in k, but it's kind of polynomial in n still, because the wild stuff is just changing the exponent. But the more interesting thing is that actually if you fix k, and this is the graph minus algorithms that have these ridiculous constants, there is a polynomial time algorithm. So there's some ridiculous f of k, this is the thing you don't want to look at, and then you can in cubic time solve the k-disjoint paths problem. Now this was improved over time. So the first improvement, as you can see, kind of came very shortly after their series of papers finished, which got this down to quadratic time without really changing anything in this f function. And then the most recent improvement, this is from 2024 by Korhonen, Michal Pilipchuk, and Janos Termulis, got this down to near linear time. So n to the 1 plus epsilon for some small epsilon is the runtime you're getting. And I'll talk about their f function a little bit later. In some sense, it's also not so good. So this is the state of the art at this point. And I want to mention that for all of these f's, nobody wrote down the function, because it's really, really bad, and it depends on some very difficult structural theorems. So what about efficient graph minors? What if we want to get rid of these, or at least give estimates for all the difficult structural stuff that is done? So this is from an article that tries to explain what would have to happen for us to get efficient bounds for the graph minor stuff. And this is specifically speaking about minor testing or k-disjoint paths. To actually get good bounds and efficient algorithms for these problems, you would have to essentially reinvent or redo the entire graph minor structure theory. So that's a lot to ask. Turns out over the last few years, people have done that. So here's kind of the points. Kind of since 2015, people have really been working on getting all these bounds down. So the first thing, I'm not going to define all of these, but just to have some reference. The first thing that kind of happened was that Chuzoy, together with some co-authors, started working on the low-level stuff like the grid theorem and the flat wall theorem. So this is the first kind of batch of stuff that happens around the middle of the middle of the 2010s. And then very recently, kind of in the last few years, people have been improving And this is from last year, the graph minor structure theorem. And here I have something called wall homogenization. I think this is not really clear to most people what this is supposed to mean. I will at least mention where it comes in, but I don't have time to explain why this is like super fundamental for what we need to do. But by now, we have everything with good bounds, and everything here is kind of a lie. But I'll get into the lie in a moment. But by good bounds, I mean all of these theorems by now have polynomial bounds. And we actually have some tools that are kind of new, that do something more than the original graph minors, in some sense, prove stronger variants of theorems. And I'll get into at least one of those kind of during the second half of the talk. So what are our results? So how do we improve on the timeline that I've shown you? So first I want to kind of mention that this result by Kohana, Mihalpilichuk, and Stamoulis kind of goes around this quote. I'll mention a little bit more about that to compare once we put our stuff down. But I want to mention that this really kind of shows that maybe this intuition is not entirely true. So what we were able to do is to show that minor containment and also k-disjoint path, if you are searching for a minor with k vertices, can be solved in 2 to the 2 poly k quadratic time. So this is, as far as we know, the first time anybody has given an explicit or as far as explicit without giving the concrete polynomial, but an explicit runtime for this f and for this problem at all, including this f of k here. This is again not explicit. I'll mention in a moment why. So there are some conjectures you can kind of try to marry these two, and all of these I've kind of heard from various people, so these are not particularly original, but it seems reasonable to say that you can probably get one more exponential lower, so it should be possible to do this in 2 to the poly k. And maybe it's possible to also just keep this 2 to the 2 poly k, but go near linear. This is a little bit unclear, as I'll say in a moment why it's unclear. And kind of the goal would be to say, let's try to do it in linear time with a single exponential bound on this f. This is kind of, I don't think, I've talked to some people about this, I don't think anybody has an idea how to get there, but that's the goal, right? So a little bit about this other result before I get into what we do. So instead of going through all of graph minors as we do, they kind of avoid it by doing, first of all, logic and some clever tree decomposition stuff. So they kind of dynamically compute a tree decomposition, and while they're doing this, they're trying to figure out if there's something they can forget to reduce the instance to something smaller. This is very expensive in the sense that they do have to use Courcell's theorem over and over in their algorithm, and this immediately makes whatever they have here galactic. And we know that we cannot get a better Courcell's theorem in the sense that you will not get a non-galactic bound. So we know this always has to be a tower of exponentials depending on what you're putting in, and the formulas they're using are not exactly small. So this is still galactic, so it's not clear how to do this galactic thing and turn this into this algorithm, because what we're doing is really trying to follow this quote, trying to redo the structure theory more efficiently instead of finding clever tricks. So this is kind of two sides of the same coin, trying to do everything from scratch, and this result with a near linear time kind of does clever tricks with logic and tree decompositions. Yes?
But they do use the vertex thing as a black box.
Yes.
Okay.
Essentially what they do is they encode a formula in MSO. This is not entirely trivial to say that there is an embedding for what I've found up until now, and in this embedding there is something irrelevant. So as they're building it, they're saying, okay, at this point there's something irrelevant. Actually, I can delete it and do everything over again.
So graph minor still lives inside of their algorithm.
Graph minor does live inside of there.
Okay.
Yes. But I think with everything else being efficient, the bad thing is Courcell. Okay. So I'm going to get into a little bit more fluff to kind of slowly get you into the meat of this talk. So the first thing is, I need to somehow explain to you what actually the tool is that we're doing here. So a question I asked a slide ago was, is everything by now, does everything in graph minors have good bounds? And the one thing that's missing on the slide that I had previously was the vital linkage function. So now I need to give you some more in-depth definitions. So for vital linkages, I need one thing that we haven't discussed so far. This is tree width. So really, you can just say, okay, my graph is tree-like. This will suffice for this talk. But if you want a definition, I chose this one because Sebastian showed it to me, and I thought it was nice because some of my students are doing chordal graphs right now. So you could say the tree width of G is the smallest integer k for which there exists a tree, and a collection of subtrees of this tree such that for all edges in the tree, the two subtrees representing the two vertices intersect. And any node of the tree appears in at most k plus 1 of these subtrees in this family. But really the thing you need is this picture where you have a thing that kind of looks like a tree and all of these bags are kind of thick and there's lots of stuff in them. But there's control because you have small separators at these where these bags intersect. So the reason why I need to define this is because I want to say something about vital linkages. Vital linkages are going to be the main thing I talk about for the rest of the time. And a vital linkage, where a linkage is a set of vertex disjoint paths, is a linkage that contains all paths of the graph, and there does not exist another linkage joining the same endpoints. So I'm covering the entire graph, and there's no way for me to change this linkage into something that connects the same endpoints. So in that sense, it's vital because it's the only way to connect all of them, and I'm covering everything. So the vital linkage theorem now just says, okay, there exists some function, and for every k, every graph containing a vital linkage with k paths has tree width at most this function of k. I'm going to call the function lambda from now on. And this is just a statement that says there exists such a function. They don't say anything about what it looks like. So this is kind of a simple statement in the realm of graph minors because it doesn't have like a huge definition of everything that goes into. You just need to have tree width and the vital linkage function, but surprisingly you need the entirety of graph minors to talk about this theorem. So let me first talk a little bit about what people have done for the vital linkage function. So here, this is graph minus 21. You can see it really exists here at the end of this entire series. They can say lambda exists. And this does have, this is important for the entire series in some way because they need this idea for even this very abstract Wagner's conjecture. And people have been trying to improve this for a while. So you can again see that this has been going on for a while and quite immediately people had an idea of how to improve it, but this is because the people involved here knew the authors, so they had some idea of what had to go into this, and they were able to give the first explicit bound. The problem is we don't know what the explicit bound is exactly, so this is personal communication with the second author, this is Paul Wolin, and he says, okay, the explicit bound is something like a tower of powers of height at most 5, and there's a k to the 1000 at the top. So this is the first time we get an estimate of this that is somewhere close to nice. So the other thing that people have tried is to look at more restricted classes, specifically planar graphs and bounded genus classes. So the order of these is kind of screwed up because this first one talks about Euler genus, and then the last one talks about planar graphs, and the one before that talks about Euler genus again. But planar graphs, of course, have bounded Euler genus. The problem here is that this one just appeared on arXiv, and both of these took, I think, at least 5 years to review, something in that range. Tony can tell me because he's on one of these papers, and what he did there is pretty important. So it turns out that for bounded Euler genus, first of all, there existed an explicit bound in k, in the number of endpoints and the genus. And actually, if you look at planar graphs, let's first look here, we get a single exponential bound. And even if you look in bounded Euler genus, you still get a single exponential bound. So I have something to say about this Mazar paper in a moment, but it looks like actually, at least on bounded genus, things are working out fine. So even this estimate of a tower of powers of height at most 5 might be salvageable. Now the question is maybe you can get polybounds, right? Everything else has polybounds, so why does this not have polybounds? Maybe you just have polynomial tree width. Let's look at that a little later. So here's a lower bound for the vital linkage function. There exists a planar graph with a vital linkage with 2k endpoints and tree width at least 2k, 2 to the k. This also appeared like 8 years after it appeared on arXiv, so another very long story. So what you're seeing here is a giant grid. If you know anything about graph minors, giant grids have high tree width, but the problem is that you can't really reroute this because it kind of works like a sandwich. This guy has to be connected somehow, but it clearly separates these two sides of the grid. And the way it works is that it keeps iterating in this way. For example, here, this guy separates these 4 quadrants of the grid afterwards. And this way it builds up on itself. There's a small note I want to make just because I noticed it at some point and I thought it was interesting. This kind of construction actually appears way earlier in the 90s. So this kind of construction was used to show that string graphs require an exponential number of crossings, potentially, in a representation. And this was pretty important because people were trying to use this, the number of crossings you need to figure out whether you can recognize string graphs. These look very similar to me. The way these kind of sandwich construction works is very interesting to me. The problem is I don't really know if there's a connection. I just want to throw it out there if somebody sees why this is the same thing. Okay, so before I get into the vital linkage function, for a reason you will probably see in a moment, or I hope you will recognize in a moment, I want to explain how the graph minors algorithm actually works. So this is for k-Disjoint paths. How do you actually compute whether a graph has k-Disjoint paths? So I'm given some graph with a terminal set t. These are the endpoints I want to connect. And now I have to ask myself a few questions. So there's a few cases, but it's not very bad. The first thing I ask is, what's the tree width of G? If it turns out that I have small tree width, then I can solve the problem via dynamic programming. So I just go up in the tree decomposition, try to figure out, are there paths connecting my stuff? What are potential paths going upwards? And I try to figure out in total, do there exist these paths, which is possible because I have bounded tree width, and there's not much to check on the separators that I find as I go up the tree decomposition. So this is kind of a nice case. Now the second is, okay, if I don't have small tree width, I have big tree width. And maybe I have big tree width because I have a big clique minor. Now there's two cases here that can happen. I could be well connected into the clique minor. And in that case, okay, if I'm well connected from my terminal set into the clique minor allows me to route all the paths I need. So what I want exists. Otherwise, there's a small separator. This is supposed to be a small separator between my terminals and the clique minor. And that means that no matter how the solution, if it exists, would run, it's missing one of these vertices because inside the clique minor, there's not really much to distinguish them, right? I can just route through all of them, and if the clique minor is big enough and the separator is small enough, I don't really need all of the clique minor. So here there's a vertex that I can delete. It's irrelevant to the solution if it exists. So if you've heard this before, this is kind of where irrelevant vertex as a term comes from. And if I figure out I can delete this, then I can delete it. I don't know if there's a solution, but my graph just got one vertex smaller, so I can iterate and ask again, maybe my tree width is now low. Could be. If I keep deleting stuff, the tree width could now be low, because in particular here in this case, I'm deleting stuff from a clique minor. Or the tree width is still big, and maybe this time I don't find a big clique minor because I kept doing this until I've killed all big clique minors. In this case, there's a magical black box that helps. So let's look into the magical black box for a little bit. The magical black box is a little bit more work, but then we'll finally get into the vital linkage stuff. So I'm putting up the timeline again, and here I'm going to omit a lot of details, and this will continue throughout the rest of this talk, and opening up this black box by looking into the individual parts of graph minors we need. So we start with, I'm already excluding a clique minor, and I have large tree width. This is the part of the diagram I was in. And because I have large tree width, I contain a large grid. So this is the kind of grid you had in this counter example, right? This large thing that kind of looks like it's very easy to route through it, let's say. So this is the first thing I need. I have large tree width, I have a large grid. Now what I want to do is I want to find a large subgrid that is almost planar in some sense. In the sense that if I were to embed the graph, I could embed this part in a planar way and I know nothing jumps in. This is what I mean by almost planar. This irrelevant vertex will be relevant in the future.
What is the meaning of the sign after the irrelevant vertex? That is the real question.
That's a good question. It's an arrow. So now I've found a large, almost planar grid. And now the vital linkage function tells me that there should be no large grid if I have a vital linkage. The problem is I don't know if I have a vital linkage, right? So this is a nice theorem to have, but how do you figure out whether you have a vital linkage? I will sadly not be able to tell you, but it's important. Now, here is the one part where I can tell you we do need wall homogenization here, because in this almost planar thing, I need to figure out that the middle is irrelevant, and for this I need to know what's actually happening in the wall, like what's attaching in the faces of the wall. And to control this, I need to make sure that the subwall I'm looking at looks the same everywhere. There's ways to prove that such a wall can be found that were previously shown using exponential bounds. And this is from the beginning of this year. This is from February. We were able to show that you can also do this using polynomial bounds. So this is where this comes in. I just want to mention it because this is one of the papers we needed to do to actually do this project. Okay, so somehow the vital linkage theorem is important here. Now, how do I look at the vital linkage theorem? It turns out the diagram I gave you for the Graf-Meiners algorithm is very similar to the diagram you kind of need to look at for the vital linkage theorem. So let's look at this diagram again and forget some parts. So I'm not in G with a terminal set T, I'm in G with a terminal set T, and also there's a vital linkage. Also, I can forget all the stuff about having small tree width because I don't have small tree width. I'm trying to say, okay, if I still have big tree width, then stuff happens. So I have some big tree width, and then it could be that I have a big clique minor. If I have a big clique minor, then either I'm connecting into it and somehow I didn't really need, if it's big enough, then, wait, I've confused myself. A big clique minor, I'm connecting into it, then why am I vital?
I mean, your graph is nothing but the clique minor, right?
Yes, at that point my graph is tiny and then I have small tree width actually. That's fair. And if I have a small separator, I find an irrelevant vertex, and kind of the joke with the irrelevant vertex is that it can't really be irrelevant, because if it was irrelevant, then my linkage would not be vital. Irrelevant means irrelevant for the existence of this connection. Now I've opened up a new black box. I call this not magical, but topological, because now we need to get into the meat of the proof. So how do I deal with a case where I don't have a clique minor and have to do something now on a graph that still has big tree width, but I can't use these quite nice arguments about big clique minors? So for this, I need to introduce, I think, probably the most important definition. It's not that complicated, that talks about how the terminals are distributed in the graph. So I want to say that the bidimensionality of a set is the order of the largest grid rooted at this set. And you can kind of see that this in blue is trying to model the minor via a minor model. And when I say rooted at X, this just means that in the minor model, I have to somehow include one of the terminals. It doesn't have to be like here in this corner that this is kind of an important vertex. If I delete this, then the model doesn't work because I need to connect these two parts. It could be that this is kind of living somewhere outside here and I'm just kind of collecting it. This is what I allow to be a rooted minor in this sense. And the bidimensionality just says, or is high if the terminal set has a lot of structure in the sense that they're well connected into some high tree width object. This is what bidimensionality is trying to capture. And in a moment, we'll see kind of where the idea for this comes from. So bidimensionality is important because we want to use a version of the Graf-Meiners structure theorem, which I'm going to present to you next, which relies on looking at this bidimensionality. So this is the other thing we had to prove for this. This is also a paper from February with Evangelos Protopapas and also with Sebastian that says there exists some polynomial such that for all B and R and every pair consisting of a graph and a set R, one of the following holds. I could have bounded tree width in B and R. I could have bounded bidimensionality. This is where B comes in. B is trying to be bidimensionality. It could be that not bounded, but unbounded bidimensionality. It could be that I have a large red grid, or I guess in here it's a pink grid. Or I have a polynomial sized clique minor. As we saw, having a big clique minor is helpful for us in some ways. So far we had bounded tree width, this is nice. We had polynomial sized clique minor, this is nice. And large bidimensionality is also helpful for us. And the last option, this is where we really need to put some work in, is that we get a structure decomposition. So it could be that we don't have any of these three things, but there is some set, which I'm going to call apices, that is small. This is this polynomial f, small in B, so just the bidimensionality, not the number of terminals, but their bidimensionality. And there exists some grid minor in my graph. This is gamma. And around gamma, there exists an almost embedding that controls R in a particular way. So I delete the apices first, and now I look at some grid, and what I want to say is that the rest of the graph with respect to this grid embeds in a surface of bounded Euler genus. This is again bounded by this function f in terms of b, just by the bidimensionality. And all I need now is that the number of areas in this embedding that are fairly non-planar, but still controlled, is bounded also in the bidimensionality and this function f. I'm going to call these disks vortices. And you can kind of imagine that whatever is outside of the vortices is basically embedded in a non-crossing way. And the way that R is controlled is that I either have R as one of the apices, or a vertex from R as one of the apices. This could happen. This is not so bad. There's not that many of them. Or the rest of them, whatever is not captured in A, is inside of these vortices. So why is this helpful to me? Well, there's not that many vortices, and their structure is controlled and has kind of a nice boundary to the rest of the graph. So I can kind of corral them into the vortices, do something with them there. This is what we'll do next. And then say, because everything is in a small number of faces in the embedding, this must still have bounded bidimensionality once I've done everything that I want to do to make this handleable. So how do I do this? So I will now try to explain to you how I go from this weird structure here to something that is embedded in a bounded genus surface, properly embedded, not this basically embedded notion, and where there is no longer any vortices but instead faces. So how do I reduce to embedded graphs? The first thing I have to say is every step here is extremely oversimplified, but that's fine. So the first thing I'm going to apply is the structure theorem I just showed you to a graph with a vital linkage, and R is just the endpoints of the linkage for now. So the interesting case to me is if I get this awful thing. The first thing I need to get rid of is apices. Why? Because I really don't want to guess about what the apices are doing, and I want to look at an embedded graph and control something nicely. These apices could jump from one part of the embedding into the other. This is not really nice for me to control. So the first thing I have to figure out is, what do I do with an apex? Here I made this pink. This was probably not the best choice, but imagine this is an apex. It has some connections, but the green part is the linkage, and the green path here is the only part of the linkage that's touching this single vertex, right? It's a single vertex, so in the linkage it has degree 2, so the only connections that are super interesting to me, because I'm looking at a vital linkage, are the connections that this pink path is making on the green path. So I want to know what happens to these two touch points on the surface. So what I will just do is to kind of pluck apart the apex there and just drag it down to the surface. So there's kind of two things to look at. First of all, I could be dragging something into a vortex. This is great. I want my stuff to be in vortices. So this I'm very happy with. And now I've kind of split my path into two, right? I've somehow created a path by splitting it apart. So this is now the new path going wherever it was previously. And on the other hand, I could be pulling something down to the surface. This is kind of annoying because once I do this, now my embedding doesn't have this property anymore that stuff is corralled into vortices. But actually I can just put a vortex around it. It's kind of a trivial vortex. It only touches the embedding on one guy. And now there's like a degree 1 vertex living in the vortex, but it's a vortex. Importantly, because I have a bounded number of apices in the bidimensionality, I'm not creating that many new vortices, and I'm not creating that many new paths. But I need to be extremely careful to not do this too often, because if I keep doing this, I will constantly create new vortices that I will need to create structure for, and I can't afford to do this repeatedly. So while this looks nice, this is something we can only do at the very beginning. From now on, I'm trying to never create apices again, at least not ones that see stuff on the surface. So this was the first step. The next step is I really need to find around my vortices many concentric cycles that kind of enclose it in a nice way. This is also one of the reasons why I don't want to create new apices or vortices, because if I create new apices or vortices, I have to redo this step, and this step is expensive. So this is one of those steps where I'm oversimplifying a lot. So technically there's some ways to do this in the literature. The problem is they don't work for us quite as they're written, because they do create new apices. So we have to get around this in some way. But the idea is essentially to just kind of cut down the surface as long as there's short curves separating stuff or connecting stuff. And once you're done with this, you get a lot of cycles around vortices, and it may be that the cycles around vortices contain other vortices, but then this vortex, along with its cycles, is completely contained between two of the cycles of another guy. I want to mention that we have to do this because the structure theorems we're using, the ones that have polynomial bounds, can't actually give us lots of cycles around nests, because kind of part of their proof is to try not to make this too large. So it's kind of antithetical to try to use them to get these cycles, even though you naturally get some cycles, to get the amount of cycles we need. We need as much cycles as there is amount of non-planarity happening in the vortices. And that's just something that our structure theorems with polynomial bounds cannot do. And to get good bounds for the linkage function, we of course want to use polynomial bounds, or at least the best that's available to us, so we kind of have to redo the embedding at this point. So now we have this stuff around the vortices. Why do we want the stuff around the vortices? Because we want to control vortices, and they should all look the same in some way. What do I mean by this? So a vortex you can imagine is kind of a cyclic ordering, and on the cyclic ordering we have a tree decomposition that is actually just a path. And every part of this path is rooted onto the boundary of the vortex. And the problem is this is something you get, but it could look very not so nice. So there could be some very big bags here that intersect a little with a small bag, and then it goes to another big bag, and then a few small bags connected to each other. This is not really nice to talk about. We want to normalize this in some way and ensure that there's some connectivity through them, right? We're working in a graph that has a vital linkage. What is the vital linkage doing in here? Or at least what are linkages doing in here? So in this step, we're using all of this structure around the vortices, all of these cycles, to push them into the vortices and then create linkages. So what we want to get is a path decomposition where all the intersections between the bags have the same size, and there exists a linkage going through the entire path of this path decomposition. Again, this kind of exists in the literature, but the way it's proven makes apices, so we have to redo this, and also this funky thing we did here where we stacked cycles and cycles is not in those proofs, so we have to redo this part as well. So everything is very strange until we get there, and now you could say, okay, wonderful, there's another part of the literature that kind of does something here. The problem is that's the part that's by Robertson and Seymour and gives us bounds that we really do not want. So we have to redo this part as well. So at that point, I'm kind of skipping over 40 pages of the proof and telling you, okay, now that you have these well-controlled vortices and have these wonderful linkages inside, you want to cut them away entirely. So I've done a lot of work to make them nice, and now I want to forget them. The purpose of this is to say that in the end, my embedding will be kind of actually embedded outside. I will still have some wall left over because I may have killed some of the initial wall by choosing large sets of concentric cycles around vortices. And everything that was previously a vortex is now a face, and these are exactly the faces onto which my vertices, my endpoints from the linkage are mapped. And there's not many of them. And not many of them is something polynomial in the original number of endpoints, and something single exponential in the number of, I don't know, I think at this point we're still polynomial. Something polynomial also in the bidimensionality. So I'm...
Exponential.
No, that is single exponential.
Yeah.
Okay. Single exponential, the bidimensionality, which is fine, as we will see in a moment. So at this point, I've created a bunch of new vertices as endpoints of our linkage, so I have a lot more paths in my linkage, but this number only badly depends on the bidimensionality. So what do I do with this graph that is now essentially embedded and has a few faces on which my endpoints lie? So let's do the simplest case. The simplest case is that actually I've managed to get to the sphere, and there's a single face, and all the vertices are on this single face. And these concentric cycles I have here just come from the fact that somewhere in the embedded part there's a large wall. So I can just choose the cycles from this wall. So what I want to know is this a vital linkage? Does this cover the entirety of what I've drawn here? In this case, I have to kind of be more exact and say what are the endpoints that are trying to connect to each other. Here I've drawn something that's not feasible. For example, this purple to this purple and this blue is not possible because I'm planar. So I have to also kind of choose a viable alternative for pairing these endpoints. But we know there exists a vital linkage, so we know it's feasible. So let's do something that doesn't cross each other. And now you can kind of easily see that actually I didn't need the middle cycle, because I can just kind of route around it. And if I have k pairs of endpoints and k plus 1 cycles in this type of instance, then I don't need the innermost cycle, which tells us that our linkage was not vital. So this instance is super easy to solve. So let's slightly generalize. Let's say we're still in a planar instance. All the terminals are on several faces. So k terminals on b faces. Now it gets more annoying, because while there's a disk in the middle, the faces kind of allow us to walk around the faces and create, in some sense, the kind of crossing I was previously trying to avoid. There's something that's topologically interesting happening that I can't just model by saying I'm going to try to take a detour along this cycle and then I'm done, because I have to somehow skip over other paths in some parts of this picture. That's annoying. Now, finally, I can talk about the stuff by Jim, Tony, and Bruce. And that is, there's a theorem that tells us if I take a non-separating boundary-to-boundary curve in this picture, or in general in a surface, then if there is a solution for my linkage problem, there is also a topological solution in which each path crosses this curve at most twice. The key word here is topological. So we have some graph that's drawn on here. This is a solution, and the drawing gives us also a topological linkage in a sense. But what this theorem gives us is just some curves that connect these endpoints. This doesn't have to correspond to the graph, but it might still be nice. So let's choose some curves on a way that kind of separates out going around one of these paths, and think about how many parts of our actually existing linkage actually cross over these curves. So it could be that a lot of the embedded solution crosses over this. And here we can actually say if it's really a lot, something exponential, then you actually have enough structure here, because you have a lot of paths going through a lot of cycles here in the middle, then I have enough structure to recover the topological solution that this theorem by Jim, Tony, and Bruce give us. So I can kind of cheat by saying, if there's enough going over there, I could have actually rerouted, and thus there was something irrelevant, so there can't be that much going over there. So there can't be that much going over there, and because there's some bound that I can use, I'm not going to compute the exact one, but there's some bound that I can use, I can just cut through this part and say, okay, I cut through this part. Cutting through this part just creates a few new endpoints. I just drag them down to the boundary of this disk in this way. And now I have a few more endpoints, a few more parts of my linkage, and can try to iterate. So the problematic part about the iteration is, of course, that because I've created new endpoints, I have new paths that now are also going over this curve that I'm drawing. So this keeps increasing. The bound that I consider not that much keeps increasing, but I've started with some bound on the number of faces. And now recall the way we got our embedding. We had something embedded in a surface with a bounded number of faces, or a bounded number of vortices initially, that we reduced to a bounded number of faces. So we do have a bounded number of faces to work with. And what we ultimately get once we've iterated away all of these faces is a planar instance embedded on a disk, and now we know what to do. So how much does this put us in the red? Well, this ultimately will end up getting us an instance, a planar instance, with 2 to the poly of the bidimensionality times poly of the number of terminals, initial terminals, more terminals. So importantly here, this was what I was checking with Sebastian. This k, the number of terminals that I give as input here, already has polynomial in the initial number of terminals, but is single exponential in the bidimensionality. But this just works out because exponential functions are nice. So what it says here, if you fold this out, would be 2 to the poly of b times 2 to the poly of b times poly of k, where k is the initial number of terminals. So this works out for us. And in fact, what I just explained to you, this cutting through this thing, doesn't really care about whether or not these strips are planar in some sense. What you can look at is, what if I try to represent my entire graph, my entire embedding on this bounded genus surface by just attaching strips to a disk? So you can kind of do this by saying, the way I would realize a torus would be to say I cut some hole into the torus, and this actually corresponds to a disk with two strips that kind of jump over each other. This would be my handle. And the Mobius strip actually is exactly this type of object. I can just kind of choose some area to say it's a disk. I think this was shading. This is kind of done badly. But let's say I choose some area here in the middle that's a disk, and then I can see the rest as a strip that twists once and then attaches to the outside of this disk. And this way I can build my entire surface, and my faces now are where the pink vertices lie on the rim. And now I can do the same thing. I can cut through this strip and say how much stuff is going over this and cut it away. And keep iterating until I'm done with all these strips. So I have a bounded number of faces. My genus was also bounded in the bidimensionality. So yes, I have a few more strips, but this is only genus many. The genus is not that bad. So ultimately we still get this nice bound that is 2 to the number of strips that we have here times number of terminals, or poly in the number of terminals. And thus this actually generalizes to bounded genus, not just bounded many faces. Okay, so let me update, and this is the last thing I'm going to talk about, let me update the results page. So the results page should now say the k-Disjoint Paths Problem, and I'm not doing the minor one, the k-Disjoint Paths Problem for a set of k endpoints with bidimensionality at most b can actually be solved in 2 to the polynomial of bidimensionality, but it's only single exponential in the number of endpoints. And the reason this is true is because we get this nice bound on the linkage function that tells us actually the exponentiality comes from the bidimensionality and not the number of endpoints. And I think that's it for me.
Thank you. Any questions?
There were some claims that you could do like n log n for minor testing. What's your opinion on?
I don't have an. I think these are kind of fundamentally incompatible in some way. So I think Sebastian asked about this in the middle of the talk. This kind of itself relies on the relevant vertex. So this thing that we're doing in here is used to find this irrelevant vertex. They're kind of saying I have a formula that says there's enough stuff around something that it certifies that actually if you try to get into there, you would violate this vital linkage function, and thus something flies out. But this needs inherently to know what this function is. So you're encoding this fact somewhere deep in a formula, and then you're throwing this fact into Courcell. What I can tell you is I don't know if you can get this down. I believe them in the sense that if they claim it, I mean, this is probably not a problem of doing this. This is a problem of doing this dynamic programming over tree decompositions, is my bet. I don't actually know.
Yeah.
But I believe them that they can probably do this. But I can tell you that I don't think this is so easy. Any of these is easy at all.
Well, the last one is pretty.
Oh, the last one is particularly hard. But I think this one is probably just asking, are these two compatible? And I think maybe you can do it, but I don't think like there's a direct way to just stick one into the other. Even with the better linkage bound, you still have to stick this into Courcell, and then it's still galactic.
Can we do the group labeled version of this kind of problem?
You can if you want to. The general impression is that, I mean, you will need some tricks, but we're not doing anything that's super specific to not having labels or anything like this. We're not having weights. The methods we're using are not, they don't abuse any of these facts that we're not working with group labels or anything. This is definitely not easy to do, but you can probably do something here. I don't want to claim anything. I'm not working on it, but
I mean, long standing, right?
I mean, he doesn't get these bounds.
Yeah. Right.
No, he has a group labeled disjoint paths algorithm. That definitely exists. It's just not with these kinds of bounds.
Is there any chance that like some completely different technique like color coding or whatever may just come in and solve some of the issues?
So are you asking if there's a completely different proof, or
Different approach might like do
To
we always
solve-
need all these similar framework where you or
I mean, obviously there's some stuff you can do that's not directly graph minors, but it kind of uses graph minors. The problem is that this looks like it doesn't have much to do with the core of graph minors, but it really uses all of it. Like there's nothing you're not touching, basically. I think we're kind of at a point where we've invested so much in this method that probably maybe there's a way to do all of this separately. It will probably not immediately give good bounds, and then you would have to work hard to get good bounds, and then you would have to see and compare if they work. I don't think anybody has an approach to prove graph minors without doing Robertson-Seymour graph minors. So maybe what you're asking is not like, can I do graph minors? Maybe what you're asking is, how do I get from here to here? There's definitely some tricks you can use that we're not exploiting that are, I don't exactly know what color coding is, but I bet there's some tricks there that we could exploit. But in terms of actually proving the fundamental theorems, I have some belief that there might be something that exists, but the question is it worth investing to actually find it?
Maybe I can add two
Yeah.
things to this. The first one is the only other like general framework to deal with these kind of routing problems that I know of is Schreiber's algorithm, which would be XP, and it's still inherently topological. And then the other one, every single known method. So for some of these we know, like on planar graphs we know it's linear and single exponential, and for bounded genus we know it can be done linear. But every single method, including the one up top, this is why I don't agree that this doesn't use the graph minor framework. Every single algorithm we know uses the vital linkage function. This one does use the vital linkage function.
Yeah, it does use the vital linkage function. I'm just,
So
my
it
argument was
uses
that,
graph minors. Yeah.
yes, but you can do something about this that doesn't have to do with redoing graph minors.
That's true, but you need to use fundamentally the same framework.
Yes.
So it's really unknown.
another question I like thought about, like you had this corollary for minor testing, right? And
It's not,
kind
it's
of
really that this is a corollary of
yeah, or whatever. So the could that be some okay? So the other direction, like when so this gives me the, I mean, because of your theorem, if k is certain like log of n, then you have a polytime algorithm to do that, right?
yes.
And like, and of course, if k is like linear, then it's mostly empty complete. So I wonder whether like there's any like bound where we know whether we can reduce this empty complete regime, like
That's
log n, or
Good question.
like if it's bigger than log n, then is it already empty complete, or right?
That's a good question. I don't know the literature there.
I think the problem is also we don't know the degrees of these polynomials, right? They're massive.
Well, I think the problem is that the theorems we're using have very bad estimates, because we at some point said, okay, if we try to tease everything out, it just takes too long. I think you can get like reasonable estimates, as in it's not, the degrees of the polynomials are not themselves galactic. Maybe like 10,000, something like this. No, I think this is possible. So one of the main blowouts is the structure theorem we're using, and I looked into why we got good bounds for the original polynomial GMST, and this is just because I at some point, to figure out bounds, I really dug deep into the proofs and like dragged everything out. If you drag everything out, then you can get better bounds. I think there's a similar thing with the odd minor thing that I did with Mugen and Gonu, that the bounds would be bad if you computed them like roughly by just taking like the black box from the polynomial GMST. But if you actually looked into what the black box is doing and computed out what actually the bounds are, it would get a lot better. The question is just, is it worth it? Because we're not talking about single digit or double digit or even triple digit. We're talking about improving something to like 1,000 something. And the question is this worth it? I don't think so.
How long is the proof, by the way?
160 pages?
160?
160.
With references, but yeah. I don't think that really makes it.
All right. Any other questions? So if not, let's thank the speaker.